What? Oh, syllables.
Arigato, yeah.
All right, today we are learning about divergence. Okay, here is the explanation. Divergence measures the change in density of a fluid flowing according to a vector field. How would the density change? Like if the temperature changes maybe or something, yeah?
Like air. When it's going fast.
So anyway, so to compute divergence, it's quite easy in the notes. Here, let's write this on the board for the people who are watching. The divergence of a vector field is, look, it's so easy. It's the partial of V1 with respect to x plus the partial of V2 with respect to y plus the partial of V3 with respect to z. So that's how you compute divergence, and number one, you're just going to compute divergence. So let's use the example in number 2. If you have a vector field, which is, what is it?
X plus squared 3d squared.
What is the divergence of this vector field? Well, that's easy to do, right?
Yes.
What's the partial of this with respect to x?
1.
What's the partial of that with respect to y?
Y.
And what's the partial of this with respect to z?
6z.
Yeah, that's the divergence. Okay, but what do you do with it? Well, that's why we have the divergence theorem. Let T be a solid totally bounded by a closed surface. If the components of the vector field are continuously differentiable on T, then the flux, so again, we're computing flux here, the flux of the vector field across the surface is given by this triple integral. And then what does it say? The divergence of the vector field dx, dy, dz. So probably whatever the solid is, that's what's going to determine whether you should do rectangular, cylindrical, or spherical. Okay, so I'm going to let you do number 2. In fact, we're going to do number 2, except I'm going to pick a different solid. Let me think of a solid. How about a sphere then? So the solid will be x squared plus y squared plus z squared is less than or equal to, give me a number.
1.
No, come on, that's weak.
4.
Okay, 4. So that would be a sphere of radius 2 then, yeah?
Yes.
So it says, what are we trying to, out of the solid. So the divergence theorem computes the flux out of the solid according to that vector field now. Okay, so we already computed the divergence. At least let's set up this integral. So triple integral. Now we already computed the divergence of this. Let's just use that one, plus 4y plus 6z. And then, what kind of coordinates is, which one should I use? Should I use rectangular, cylindrical, or spherical?
Spherical.
Okay, there you go. So do you guys remember? Rho squared sine phi d rho d theta d phi.
Also, we gotta know every one of those from last chapter.
Exactly. So when you have a sphere of radius 2, okay, so what are the limits of integration for rho going to be? 0 to 2, and then theta 0 to 2 pi, and then phi 0 to pi. See, everything's constant. Okay, but then we're going to have to change these to spherical. And remember how to do that? That was on the last test, right?
That's the thing.
So again, if you forget, draw the box. Wait, I'm trying to concentrate. Some of you, well, you had it memorized, that's why, yeah? Okay, but I don't have it memorized. So draw the box. Okay, so this is rho, this is theta, and that's phi. So you have a right triangle there, a right triangle there. So if this is phi, wouldn't that be phi?
Yes.
So wouldn't this be rho cosine phi? And this would be rho sine phi. And then for this triangle, this would be rho sine phi sine theta. Right, you guys did this, right? And this one here would be rho sine phi cosine theta. Yikes. All right, so what do I substitute for y? Rho sine phi sine theta. And what do I substitute for z? Rho cosine phi. So what kind of integral would we get here? Here, let's actually do this. Let's see what kind of integral we get. Oh, you dummy. 0 to 2 pi, 0 to 2. So 1 plus, should we? Rho sine phi sine. So if you distribute the rho squared, that's not going to be so bad, right? And then you integrate with respect to theta, that's not so bad either. And then you integrate with respect to phi, that's not difficult either. So this is easy, this integral. Oh, so we still haven't come across that secant to the fifth one yet. I think that's in the next one, or is it this one?
No, it was last night's one.
Really?
Yeah.
Oh, did you guys do it then?
Yes.
Yeah.
You remember how?
Yeah.
Maybe you better put that in your
Easy.
notes.
So you're trying to get like the volume of the sphere.
No, we're not computing the volume, we're computing the flux coming out of the sphere.
How do you have 2 pi?
Wait, what do
You mean theta?
Yeah.
Because theta is this is theta, right? So when you integrate, you gotta go all the way around, right? 0 to 2 pi.
No matter like.
Wait.
how hard.
Okay, well, x. I thought we were done with this
Like,
already.
what if you only want a small portion of the volume?
Oh, then you gotta integrate over whatever the t is.
So well, how do you know what it's asking for?
Because they said it's coming out of the sphere.
That impact like.
Oh, I just made that problem up. So like tonight's one, it's coming out of like a cylindrical can, yeah? That's what that is. Look at number 2.
Wait, why, how does density even relate to flux? I don't understand.
The density of the fluid.
And it's changing when it's flowing out of that into like another.
No, because, well, I'm thinking, see, you guys, your experience with flux, you told me, is like magnetic flux. I'm not really even sure what that is, but I think flux, I think of a liquid flowing through a membrane.
So it's bio.
Like coffee going through a coffee filter or something like that.
Biology.
No, so if you do that,
Wait,
how
what?
do you know if it's a cylindrical thing?
Well, that's why you see, so you gotta know the solid. See, this one, the one you're gonna do on your homework tonight, says out of the solid, so that's a cylinder, right? This thing here, this one. X squared plus y squared equal 9. That's a cylinder, right? But then less than or equal to that, so everything inside it. But then z is between 0 and 1, so it's like that. It's a can. So tonight's one is not going to be a sphere. Tonight's one is going to be like a can like that.
Then you use.
So then probably I would guess cylindrical, since it's a cylinder, yeah? Cylindrical would be the best way to do it.
Right.
But then, what if it was flowing out of a,
Rectangle.
yeah, then probably rectangular would probably be the best one to use.
What
Yeah.
if it's coming out of a cone?
Oh, well, you saw the test.
Spherical.
When did you see the test? Who told you about this? Roy Sam? Chen Yi Hu? Give me some names.
What did you say? What did you say? Oh,
If it's flowing out of a cone.
If it's coming out of a cone,
right there.
then
Use cylindrical.
probably cylindrical. I don't know. We gotta look at the integral and figure it out.
Roll out,
I think cylindrical would be easier. Cause the equation of a what do you call it? Quadrant cone is like z squared equal x squared plus y, something like this, right? So since you're gonna have that, probably cylindrical would be the way to go.
Cylindrical is the same thing as polar, right?
Polar with the z coordinate, no. Polar is a two-dimensional coordinate system. But if you add the z to it, then it becomes three-dimensional.
So the triple integral of polar.
Yeah. Cylindrical, we call it.
Yeah,
Yeah.
okay.
Right?
See, it's easy. So like the first four problems, come on, if you cannot compute partials by now, just go home, right, without even cooking rice. Number two, though, you gotta actually compute an integral. It shouldn't be difficult. Okay, we're gonna play one game, and then we're going home already. Oh, look at that. Wait, let me start uploading this video to play before we play the game.